We will now look at some useful LTI systems, and first we will look at minimum phase systems. So a minimum phase system is defined as a system which has all its poles and zeros located inside the unit circle. As an example, we look at this system h of z, which has a 0 at 0.5 and a pole at 0.9. And as we can see, both of the 0 and the pole are inside the unit circle. So this system is minimum phase. Now the inverse of h of z is this system, right, where the pole becomes the pole becomes the 0 and the 0 becomes the pole. And for a minimum phase system, if h of z is itself stable and causal, right? So if we are given that h of z is stable and causal, here the pole 0.9 is inside the unit circle, and we are also given that it's a causal system. So if h of z is causal and stable and its poles are inside the unit circle, its inverse system, because uh, for h of z both the zeros and the poles are inside the unit circle, when we invert it, the inverse system will also have its poles and zeros inside the unit circle, and it will also be a stable system. However, the definition for a minimum phase system, which we will remember, is that all its poles and zeros lie inside the unit circle. Now let's look at the process of all-pass minimum phase decomposition. And we will see how this would be useful and what its applications would be. So given a rational system function, we can decompose it into a combination of a minimum phase system and an all-pass system. Right? So our given h of z can be decomposed into these two systems, a minimum phase part and an all-pass system part, and they are then placed in cascade. Now, what are the steps of the decomposition? So let's try to understand the steps of the decomposition. So our h of z is a stable system. So its poles are inside the unit circle, but it may have zeros outside the unit circle. So let's suppose it has a single zero outside the unit circle, right? So, and since it's outside the unit circle, then the location could be is given as z is equal to 1 over c conjugate, where magnitude of c is less than 1. Right? So 1 over c star would be the 0 would be located outside the unit circle. Okay. So we take the 0 which is outside the unit circle, belonging to h of z, that 0 we separate it out, right? And we write our hz in this form. Okay? So this 0 factor, which has a 0 at 1 over c star and it's outside the unit circle, this is that 0 factor, this is that 0, and this is the remaining part of h of z, consisting of all the other poles and zeros which are inside the unit circle. So it's just a way of expressing h of z. We have expressed h of z as the rest of the poles and zeros, and the one which was outside at 1 over c star, that 0 factor 0 we have written like this. Okay, so we're going to take that pole, that 0 out of h of z, right? We will think of as taking it out. Then now if we now look over here at this expression, this h1 of z is clearly a minimum phase system. And why is that? Because the zero that was outside the unit circle is this part, and the remaining part must be minimum phase because, as we said, the system was stable, its poles were already inside the unit circle, and the remaining zeros are included in the H1 of Z, and so H1 of Z is minimum phase. Now, the next step that we do is that we can write this H of Z in this form. We multiply and divide by this factor 1 minus C Z inverse. So what we're doing is we are introducing a pole at location Z is equal to C and a 0 at location Z is equal to C. So we will see that the 0 is actually introduced at the conjugate reciprocal position of the 0 that we had taken out from our original H of Z. Okay, so that was at 1 over C star, and this 0 introduced is at C. Okay, so this will get more clearer, right? We will look at the remaining steps and we will look at an example also. Now we wrote our H of Z in this form as we saw in the last slide. Uh, the 0 that we had earlier moved outside of H of Z, that is factored it out of H of Z, that 0 was located outside the unit circle. Then we have added this term, a pole at C. So this whole term is an all pass system, right? So because there is a 0 at 1 over C star and a pole at C, a conjugate reciprocal pair. So this part is an all uh, uh, pass system. And if we look over here, right, since we introduced these two terms, this is the same, our H of Z hasn't changed. But now if we look at this part, our H1 of Z was already a minimum phase system, right? And if this factor 1 minus C Z inverse, since magnitude C is less than 1, right? 1 over C star magnitude was greater than 1, and right, and that was because the 0 was outside the unit circle. But this factor here C is less than 1. So this 0 is inside the unit circle, and H1Z multiplied by 1 minus C Z inverse, this portion of H of Z forms the minimum phase part, and this term is the all pass system. So we have decomposed our H of Z into a minimum phase system and followed by an all pass system. So let's summarize the steps of the minimum phase decomposition again. So the first thing we'll do is we will look at our H of Z and see if it has any zeros that lie outside the unit circle. So we move all those zeros and make them a part of the all pass system. This one. So we will move those to the all pass system. Right? They become a part of the all part system. And then we add poles to, because the all pass system has to have poles also at conjugate reciprocal locations of the zeros. So we moved the zeros to the all pass system, then we have to these ones, right? So we move the zeros outside to the all pass system. We have to also pair them with conjugate reciprocal uh, poles at C. So we add poles, and then because we have added poles, because we add these poles, then to keep our overall system the same, right? Whatever manipulations we do, our overall H of Z must still be the same, right? We can make these factors because that's what we want to do. We want to do this minimum phase decomposition, but overall h of z must be the same. So when we add these poles at C, we must also add poles at zeros at C. And as we can see, C is the conjugate reciprocal location of the zero that we had moved to the all pass system. So we reflect our zeros outside unit circle to the conjugate reciprocal locations inside unit circle. That is that we reflect them about the unit circle at mirror positions. Right? We talked about mirror positions in our earlier example also. So if we take a 0 outside of the unit circle, we will put a 0 back inside the unit circle at the conjugate reciprocal location, and that becomes part of H min Z. So this is the 0 which comes in the conjugate reciprocal position. This is the pole that comes in the conjugate reciprocal position, and this is the 0 that we moved outside. So our H of Z has been expressed as a form of in which we have a minimum phase system followed by an all pass system. And we will look at an example of doing this all pass minimum phase decomposition, and then we will see what could be the application of doing this process. So to understand the steps of minimum phase decomposition, let's take an example. So in our example, we have a system function h1 of z, which is stable and causal. So since it's stable, its poles, its pole is inside the unit circle. So we can see that the pole is at location z is equal to 1 by 2. But the 0 is at z is equal to minus 3. So over here we see there is a 0 located at minus 3. So we'll move that 0 to the all pass component of our decomposition. So we move the 0 to our all pass system. Right? This 0 will move to our all pass system. So we move it over here. But one thing we did that we took this 3 outside, we factorized it out. So then we had it, right, 1 by 3 plus z inverse in this form. Right? So this is our 0 that we've moved out and placed it in our all pass system. Then now, because an all pass system has to have if it has a 0 at um, minus 3, then there must be a pole at minus 1 by 3. So we add a pole at the conjugate reciprocal location z is equal to minus 1 by 3. So this is the pole of our all pass system, and this is the 0 that we moved out of h1 of z into the all pass system part. Okay, and then we in our decomposition we have to have a minimum phase component also. So the minimum phase component is the rest of h of z, right? Except the 0 that we moved out to all pass system. So this is the part we're left with. So this is our pole, original pole of h of z. But because we have uh, we placed pole in the all pass system at minus 1 by 3, we have to place a 0 at minus 1 by 3 also. So we place a 0 at z is equal to minus 1 by 3 to cancel the pole that we added to h all pass z. Okay, to our all pass component, right? So to h min of z, which already had this pole, the original older pole, and then we added this uh, 0 at the conjugate reciprocal location. So this is our h min of z. Okay. So basically what we do is when we have our h1 of z, what we do is we take those zeros which are outside the unit circle, we move them to the all pass system. Then we add poles at conjugate reciprocal location, and we actually this zero that we have moved outside this unit circle, we move it back in also. We make another copy of it at the conjugate reciprocal position um, that we see over here. Right? So there is a zero added over here, and this is part of our minimum phase system, and this is our all pass system. And then let's see the complete decomposition on the next slide. So we've decomposed our h of z into a minimum phase part and a all pass term. Right, so our h1 of z is written as the h min of z into h all pass z term. So this is our decomposition, minimum phase decomposition, and it can be implemented by placing these two systems, the minimum phase system and the all pass system, in cascade. So now we'll also see a useful application of this decomposition process. In signal processing applications, a signal may get distorted as it passes through an LTI system. For example, when a signal is transmitted over a communication channel, then the signal SN, when it passes through a communication channel, which we could model as having a system function HD of Z, then the output of the distorting system, as it passes through the channel, the output would be a distorted signal SD of N. Now, we would like to undo the effect of this distortion, and for that we could pass the distorted signal through a compensating system with a system function HC of Z. So when the distorted signal SDN passes through the compensating system HC of Z, then we get an output, another signal SC of N. And if the compensation has been correct, then the compensated signal and the original signal should be the same. And for that, the distorting system HD of Z, its system function, and the compensating system function, they should be inverses of each other. Right? So HC of Z must be the inverse of HD of Z, and the overall gain of the system should be 1. But that would happen if HD of Z is itself, because HD of Z we would want to be a stable and causal system. So then its inverse must be also stable and causal, and that means that HD of Z has to be a minimum phase system. So even if HD of Z is not a minimum phase system, we can still find a way of um, doing this compensation and finding a compensating system. So we can do that even if HD of Z is not a minimum phase system, and we can do that by minimum phase decomposition, that is expressing HD of Z as a combination of a minimum phase and an all pass system. So we'll see how to do that. We can find a minimum phase decomposition for the distorting system HD of Z uh, following the steps that we have already studied. Right? We had already discussed. So, um, right? So we do this decomposition of the distorting system into a minimum phase system and an all pass system. Then we choose the compensating system HC of Z as the inverse of the minimum phase system that we found in our decomposition. So the H compensating Z is, or HC of Z is 1 over HD min Z, the minimum phase system that we found. And then we cascade the distorting system and compensating system to model uh, our signal passing through both of these systems. And then we have our Hg of z as HDZ into the H compensating C system, because they are in cascade. So we have GZ is as a product of HDZ into HC of Z, but HD of Z, the distorting system, the system which distorts the signal, we have represented it in this form as a minimum phase decomposition. And so instead of HD of Z, we have this decomposition over here, HD min Z into H all pass Z. H compensating system, the compensating system we have chosen as the inverse of the minimum phase that we found. So that is 1 over HD min Z, and all these system HZs are multiplied, um, because as we know, systems in cascade, their system functions get multiplied, and the result overall system function that we are left with is that of an all pass system. So that means that combining our distorting system, and if we put another compensating system with it after it as a cascade, which has this system function, the overall effect will be that these two systems combined will act as an all pass system, which means that an all-pass system allows all frequencies to pass as it is, and its magnitude response is 1. So the signal, when it passes through a combination of the distorting and compensating system, its magnitude will not be changed, and there will be no overall distortion, because the distortion will be compensated, and the signal passes undistorted through this combination G of Z, uh, right? So distortion is undone, and this is a way of correcting signals which undergo corruption and distortion. However, passing through these systems, because the overall system is an all-pass system, as it may have added some phase shift, but there will not be any magnitude distortion. So we have looked at these various systems, all pass systems and minimum phase systems, and we have seen what are some of the uses and applications of these systems, and we have seen some examples, and we will continue with some related discussions in the coming lectures. And so I will conclude the video lecture 10 at this point, and I will say Allah Hafiz. So Allah Hafiz, and I'll conclude the lecture.